Okay. Assalamualaikum and good morning to everyone. So yesterday we've covered the initial part of a distribution system. We talked about the grill selections and how to calculate the corresponding detail of the grill. So in this today's section, we're going to talk about the duct design itself. We're going to talk about the duct design. So we expect by the end of this section, you should be able to, number one, to apply the duct design framework to balance space, noise, and power using industry standard method. Then you can optimize the operational efficiency through dynamic balance point matching and variable speed control. Okay. So the purpose of a duct system is basically to transmit air from the air handling unit AHU device to each air outlet of the conditioned space. So here there are two categories for the velocity and pressure. One is that you have a very low velocity, conventional velocity. This is classified as 10 meter per second and below. The other one is high velocity, means that the main duct can go up to 30 meter per second. So what are the problem with high velocity and what are the difference between these two? Basically for high velocity means that it might subject to one is high pressure as well as noise and vibration, NVH. Right. So the higher, the faster it goes, then you're going to have issues with noise. So when you design a duct system, you have to consider some of the critical factors, which is account for pressure loss, noise levels, and vibration. Right. So these can be mitigated. These issues can be mitigated by avoiding. Can be avoided by having a good design practice, or you can use special ducts. Probably more expensive ducts are in that sense. So let's have a look for a single duct system varieties. So for an individual duct system, there's a one center fan discharged into a plenum chamber. This as simple as that. So those individual duct leads from the plenum to condition zone, typically with reheat coils. Means that the air that being distributed is a very low temperature air, but once it goes to the separated room, each separated room at the outlet, they have a heater to control the temperature. So that means if the distributed air is about 20 and you set the thermostat to 24, then the heater at the grill, which basically heats up the air that goes inside the condition room. So this is known as individual duct system. Then you have trunk and branch system. For this system, the main duct carries the total air supply. Right? Then air is split into individual branch for each zone. By having this, you reduce the work and lower power requirements. So as you can see the figure below, this one is the trunk and branch duct system. Okay. So it means that you have one main branch like that. Let me reposition my video. Right. So you have one main branch like that, and then it branch out. It branch out like this. So the main duct becomes smaller and smaller. This is trunk and branch system. As opposed to an individual duct system, from the air handling unit, you have one main branch, one size. This one size, and then from that main size, there's a branch out like this. So the key difference here is that you notice the main branch only one size, but For the trunk and branch system, this one, they gradually decrease. Let me see if I can erase all. Yeah, just like that. You see this one? It gradually decrease. This is the trunk and branch system lah. But here, only one size. And then from there, it branches out. It's a much more simpler design actually. But of course, at the same time, you have trunk and branch system. It's a reduced duct work and lower power requirements. Because as the main duct becomes smaller, then of course you can increase the velocity and so on. Then let's talk about duct system recirculation. It can be classified or categorized by how it utilizes the air recirculation method. The first one, no recirculation. It's basically 100% fresh air. From the air handling unit, it's basically, this is your air handling unit. Can I adjust my, oh, cannot. Okay, this is your air handling unit, 100% fresh air coming from the outside, goes to the air handling unit, goes to the occupied zone here, and then after that it's sucked out and removed to outside. No recirculation. So by having this kind of methods, basically require a lot of energy because you have to condition the air exactly to from outside air you have to condition. So the condition, if let's say for example the outside air is 32 degrees C, your target is 24, so you have to condition from 31 to 24. So you require a lot of energy to do that, but for some applications like hospital, factory, they require 100% fresh air. You cannot recirculate air. The second type is with recirculation. So means that a part of it will be reused. So normally for commercial use that don't involve any dangerous substance, gases, or does not require any sterile environment, you use with recirculation. This is a very common application in modern HVAC design. So means that it's very economical because let's say for example, target temperature is 24. So that means the temperature inside the room is already 24, accounting for the cooling load. So when it is recirculated back, they have a small portion of fresh air being mixed up. If you remember from our last psychometric design, we have this setup as well. So basically the amount of energy being used is much lesser. Okay. So basically, this is highly economical. It reduces the heating and cooling load. Right. So, what are the basic principles of airflow? For a typical duct system, there is a pressure change occur as shown in the technical literature. There are three key terms, right? Because if you remember back when you study pipes, I think in fluid mechanics, as the pipes, the water inside the pipes flow, there will be pressure loss. So for airflow, these are the main three terms. Basically, the first one, I start with the static pressure. Static pressure means it happens because of frictional resistance of airflow within the duct. So normally we use pressure loss, we use the standard friction loss chart, which we're going to cover at the end of this topic, how to calculate for the static pressure. Then the second type of pressure is the velocity pressure. This is the pressure that is required to move the air basically from rest and to accelerate it to the required velocity, because in your system you have a required velocity. So what is the pressure to move that or to achieve that air velocity? Because to move air, you need to have pressure difference. To push air inside your occupied zone, inside the room, for example, a typical occupied room, maybe you have atmospheric pressure, means to achieve a certain velocity, your pressure from the air handling unit need to be significant, need to be higher, not significant higher, just need to be higher from the atmospheric pressure to achieve velocity. right? And then of course you have the total pressure, which is total pressure is the algebraic sum of the static pressure and the velocity pressure of any given point of the duct system. Basically, it's a total of these two. I don't like, change the color of my pen. Maybe can do like this. It's basically the same. All right. So to do that, we use friction to measure static pressure loss. Yeah, we use friction loss chart. All right, it defines the relationship between air quantity, duct diameter, velocity, and pressure drop. Right. So this is the skeleton representation of the friction loss chart. On the normally when we start analyze our duct system, we know the air quantity and we know the air quantity and velocity, and then from there we can determine the friction loss as well as the diameter, right? So the vertical line, this one, is the air quantity, and then the incline, this one, is the velocity. Later on, we will see the whole chart, right? So from this chart, actually, we can see air quantity, duct diameter, mean velocity, and pressure drop rate. So basically, we use this to design for round duct system actually. So for rectangular ducts, normally it will have greater friction loss. To find out the size for rectangular ducts, you use this equation. It's kind of a little bit small, but if you can find it in the book, actually, you can open and check in the book. So basically, for non-round shape, we use equation 15.11 for rectangular and 15.12 for oval. Rectangular, this one, oval, this one. I will distribute this slide to you once I'm able to download the slides, later. At the same time, as I mentioned, I really suggest that you get this particular book from me, so you can actually see what's the important equation. Actually, yeah, I think maybe I'll check it out first whether I have a soft copy or not. I don't think I have a soft copy for Econ yet. Maybe I try to find the internet later on if I can. Right. Okay, this is the whole friction loss chart. I think I will check again whether for final exam this is given or not. In final exam this is given. So you will have to use this friction loss chart. Is there any zoom function? Autoplay, more, exit, full screen. There's no zoom function. I'm not familiar with Google Slide actually. Okay, so this is for a round duct friction loss chart. Means that just atmospheric value lah. If you use different gas, then you cannot really use this one. So if you refer, this is the skeleton line of the friction loss chart. So on the horizontal line, you have frictional loss. This is the air quantity in liter per second. The incline line that incline like that is the velocity. You see, this one it says that velocity, and the incline on the inclining to the left. This one inclining to the right kan. Inclining to the left is the velocity. Inclining to the right for this one should be the size. Okay, incline from left to right is the velocity, this one. Incline from right to left is this one. This is the size of the duct diameter. Okay, this one. So this is your size of the duct diameter. Okay, so kind of straightforward juga lah. Right. So when you have losses when you design a duct system, you're going to have losses, right? Either from friction, and then there are two types. One is loss in the duct surface itself, and the other one is the loss in the fittings. In the duct system, when air travel at each component, at the duct component, you will going to have losses. When you air travel through the ductwork, you're going to have losses. So this is caused by duct length and internal fitting. So in the duct length, the longer the length, the higher losses you will incur lah. For fittings, right? So normally in ducts, you're going to have teeth, elbows, and bend. So as the air travel in those fitting, you're going to have loss lah, pressure loss. So this is caused by the changes in the flow direction or change in terms of velocity. So all of this, when you design your duct system, you have to take account. So how are you going to make duct sizing? First of all, what are the things that you're going to design? You need to consider installation costs and then operating costs. We're not going to cover installation costs lah, right? But in terms of operating costs, depends on the type of fan that you're going to use. The higher the fan power to achieve the air velocity to overcome the pressure loss, then the higher the cost of the system will be, right? So when you design them, you need to consider the following factor, right? For example, the first one, you need to minimize fitting to economize cost. The higher number of fitting that you use, the elbow, bend, all those things, right, means that more losses will incur to the system, and then you need a bigger fan. And then for duct geometry, if possible, try to use circular or oval for high velocity, because for rectangular, they will have a lot of friction loss, static friction loss. So you only consider rectangular for low velocity duct system. For in terms of aspect ratio, rectangular duct should be nearly as square as possible. But the problem with square is that it will take a lot of space. So that's why you have to play around with the scale, right? For example, it can just use up to 6/1, right? Next, you need to consider safety and environment, especially the noise levels lah, and fire isolation. This one you need to consider as well. And finally, structure. The duct system need to be optimized, need to be properly braced. There are a lot of cases after a while. Normally, to hold the duct in place, they use a metal rod. Sometimes we can see they only use metal wire. So this is needed to properly install, because sometimes it will give way. It will give way. There are many times that it gives way and affect people that are currently under the duct. So it's very dangerous. Right. So what are the procedures and methods when you want to design duct? First, of course, you need to do some initial sizing. You sketch the tentative duct system and size based on the requirement. Requirement means what are the required air to go to the occupied space. Then you determine the size. There are many methods actually. There are, for example, we have equal friction, static regain, T method, velocity reduction, and balance pressure. In the book, they have equal friction method and static regain method. But the one I demonstrated here is the most simplest one, the equal friction method. If you can do your own reading for static regain method. The next step is selection and flow. You select the fan using the available data. Then you do some balancing. You need to monitor pressure drop and noise level, whether it's acceptable or not. If needed, you introduce flow restriction and then implement dampening for damper for balanced airflow. Right? Because sometimes if one room they cancel out, you need to control the fan, or either you put a damper so that you have a balanced airflow. And finally, once everything is done, you complete the final layout and calculate the cost. You also need to conduct detailed acoustic analysis, whether the sound is acceptable or not. Okay, let's have a look to an example. This is example 15.1, duct system design. Normally, your test or final exam question will look like this one lah. Yeah. So a package of air conditioner serve 4 rooms in an apartment. The schematic layout of the duct system together with the volume flow rate in each room is shown in figure 15.1a and b. Size the system using equal friction method. The duct shall be of standard circular size, so we don't need to convert them. Initial velocity is 8 meter per second. The initial velocity here is 8 meter per second. Estimate the static pressure in the index run of the duct network. So normally it will give you the branch system as well as the length for each. They should have a length. So here it's already been given lah. AB, what is the distance? BC is what is the distance? CD is what is the distance. Index run is basically the longest duct on which have the highest pressure drop. Yeah, which have the highest pressure drop. Okay, so normally in the schematic run, we need first and foremost what is the volume flow rate at the main duct. Then what is it's not the volume flow rate actually, it's the velocity at the main duct. This is the main duct at A, so initial velocity is at 8 meter per second. We need to start from there. And then we should know the volume flow rate. So for volume flow rate, it's basically as simple as adding up all the volume flow rate at the outlet, and then you should have inlet volume flow that goes in is basically equal to volume flow that goes out, right? So you need to have that data. Right, to solve this, right, first thing you need to do, the initial velocity is 8 meter per second and flow rate is 3000 liter per second. You get this value by adding up all this outlet volume flow rate. So in this case, you can get 3000 liter per second. The duct friction loss is 0.9. How you get that? You open your duct friction loss, this one, 8 meter per second, the velocity, this one, this inclined line from left to right. This is the velocity, 8 meter per second. Another line is the air quantity, air flow rate 3000 liter per second. So you have this line lah. So once you have that line, it intersects at that point, you make a horizontal line like that and read out this value. In this case, this value is 0.9. So you have 0.9. This value will retain throughout the duct network because we need to go for each and every section. We need to go to each and every section, right? We need to go to each and every section. Okay, so we need to go section by section. So because we need to identify from the F from AB to BH, AB, C to G, A, B, C, D to this one F, A, B, C, D, this one E. We need to identify all the duct size, the velocity at that particular duct. So you're going to have to need to make this table, and we have to go to each section. Basically, it will go branch out to each outlet lah. For example, AB, the volume flow rate is 3,000 liter per second, right? In this case, meter per cube per second lah. They use meter cube per second. The velocity is 8. It was given. The equivalent diameter is from here. This one, the inclined line from right to left. Okay, you read it from the chart. Yeah, you read it from the chart, get this value. So this is the equivalent diameter size for round ducting system lah. Friction chart, this one will maintain 0.9 to all sections. The length is given. Duct loss, okay, for the duct loss is equals to 0.9 times the length 2. So that's why you have 1.8. Right, this is 1.8. I think in the question there we are missing something. Actually, it was mentioned that the fitting loss, they give 1/4 or 1/4 of the total length, if I'm mistaken. Right. So I think they should have mentioned somewhere. That's why you can get 2.03. This is the fitting loss. Either you identify how many based on the duct, the length of the duct, or depends on the question. Normally they will give out what is the amount of loss. Sometimes they will give you for each T what is the equivalent fitting liters loss, or sometimes you need to refer to a table. Okay, so for AB, this is the value. You have one type duct loss 1.8. So the first part, we want to target section AB and BH. It goes to this one. So for section AB, we know the size, we know the length, right? So section BH, the volume flow rate is this one, 1.5 meter cube. So this is 1.5. Velocity, how do we get the velocity? Right? From this one, 1.5 is the volume flow rate, 1.5 meter cube per second. You make a vertical line and intersect with the friction line. So from there, you can get the diameter of your duct system as well as the velocity. So in this case, the velocity is 1.5. This is around here lah. 1.5 the velocity. Then equivalent size is about 5 to 5. This one, and I hope you can see lah. Right. This one. So you get that value for the volume flow rate is there 1.5, velocity is 6.75, equivalent diameter is 5.25. The friction is maintained 0.9, and the distance is 7, right? 5 plus 2 is 7. So basically, you have that length. To calculate for the duct loss is 0.9 times 7, you get 6.3. Right? And then for the exit, total length is 9, duct loss is total 8.1. Total fitting loss, actually you are missing a statement in the question. The statement, it says that, let me have a quick check. Where's the statement? Was missing. It says it doesn't, total fitting loss doesn't give fitting loss coefficient. How did they get fitting loss coefficient? Okay. For fitting loss is 1/4 of the total loss. No, it's not the total. Yeah, from the total exit loss. So in this case, for example, 8.1 divided by 4. So it should be 2.25 lah, this one. Where is it? 2.03. Okay, the duct loss is 8.1. So 8.1 divided by 4. So it should be 2.03 lah. Yeah, around that value for the total fitting loss. Where does it say quarter? Should mention somewhere. It's not here. Wait. Assume the resistance due to the fitting as 1/4 that of the duct leg. Actually, it is missing from the question, I think. Yeah, it is missing from the question, but actually it's in the book. Maybe when I convert the figure, it missed out this statement. Sorry about that. I will update the slide before I share it to you. Okay. Right. So once you have that for ABH, so you have the length, duct loss, fitting loss 2.03, and total friction loss. So you do similar method for the rest of the outlet. For example, the rest of the outlet for this one is ABCG, ABCDF. You see? So you need ABCG kan? So AB you already have here. So you need BC. So you do for BC section, and then you need to do for CG. You need CG section here. So for the whole one, you get the total length and the total duct loss, right? And then for the total duct loss, you can calculate the total fitting loss and the total friction loss, right? So the index run is basically the highest total loss, and in this case is the ABCDE that is having the highest loss, which is about 20 kan ni? Yeah, total loss is 20. So that will be your index run. The duct length is 16.2 Pascal because this is the loss because of the duct length, and the for fitting is 16.2 plus 27. 27 because at the outlet they said they have 25 loss at the grill. Later I will update again the question lah. They are missing some information. So this is the total loss lah. Right? Pressure drop at the grill is 25 Pascal. Okay. So this is an example how you do it. This is very important. Yeah. You need to try to do this one because definitely for final exam, this will come out. One question for this one will come out. So you need to try this question. Yeah, you need to try this question. Try to read from the friction loss chart. Okay. All right. So that is one example that I can share with you in this slide on how to design the duct system. So what we have covered so far, one is the duct design framework. So you need to consider space, noise, and power. You will use equal friction or static regain method to design duct. So in this previous example, I think we use the equal friction method, right? Equal friction method. We use equal friction method. And then we use index run to dictate the fan sizing, right? So from there we identify what is the pressure and velocity that we need to achieve from the index run. For distribution quality, basically this one we covered yesterday. For this particular chapter, we talk about ADPI, need to approach at least 100%. Occupied zone velocities for comfort need to be in between 0.15 to 0.36. At the same time, we want to keep the pressure loss below 50 Pascal for the at the green, right? So I think that should cover for this particular topics. Thank you for your time and attention, and hopefully we can see you in the next series. Thank you, everyone. Any question? Anything that you want to ask so far?
So no question.
Okay, so I think we'll conclude our lecture for today. We'll have another session next week, but remember, your test will be conducted sometime in week 14, and then the week after that is already your exam, because your exam is